So, welcome to Sotantra education. In this lecture, we are going to discuss about the concept of binary search tree, or in short, we can say this one as BST, binary search tree or BST. So, what is binary search tree? So, binary search tree is a variant of binary tree. So, what is binary tree? We have already discussed. Please go through the video lecture. We have already discussed what is binary tree. Or for simplicity, or for your recall, I am telling you. So, the tree that have maximum 2 children. So, in a tree, if each node have maximum 2 children, then we can say that tree is a binary tree. Now, binary search tree is a variant of binary tree, and in binary search tree the elements are ordered. So, how the elements are ordered? So, these are the properties each binary tree must support. So, the first one is like this: the left subtree of a node n contains values that are less than n's value, and the right subtree of a node n contains values that are greater than n's value, and both the left and right binary trees also satisfy these properties and thus are binary search tree. So, if there is a node n, then all the left subtree nodes are less than n and all the right subtree nodes are greater than n. Or we can say, in this scenario, the left side, if n is the root node, the left side nodes like this one, this side it is chotu, and right side it is motu. So, all the left side nodes are chotu, all the right side nodes are motu. So, these are the 3 properties that a binary search tree must satisfy. The left subtree of a node n contains values that are less than n's value. The right subtree of a node n contains values that are greater than n's value, and again both the left and the right binary trees or both the left and right subtrees also satisfy these properties and thus are binary search trees. So, here in place of write binary trees, it is better if you write subtrees. So, both the left and the right subtrees also satisfy these properties and thus are binary search trees. So, this is all about the definition. Now, we will see some examples. So, consider this one. So, here it is 17. So, in the root the 17, the value is 17, and the left side subtree it is 6. So, it is less than the root node 17, and here in the right side it is 19, you can see. So, it is greater than 17. So, we can say this tree or this binary tree is a binary search tree. So, it is a binary search tree because the value of the root is 17 and its left subtree is 6. So, which is less than 17, and right subtree is 19 or right child is 19, which is greater than 17. Now, consider this one. So, here it is 17. So, all the nodes of the left subtree, so 6, 3, 14. So, these are less than 17. Similarly, all the nodes of the right subtree, so it has only one right child or only one node in the right subtree and its value is 19, that is greater than 17. Similarly, you can consider the subtree with root 6. So, 3 is less than 6 and 14 is greater than 6. So, this is also a binary search tree. we can say this is also a binary search tree. Now consider this one 17, 19, 22. So the root node value is 17, its right child 19, that is greater than 17. Now its right child is 22, so greater than 19. So it is also satisfy the properties of binary search tree, and we can say this is also a binary search tree, because here you can observe 17, the right subtree values or the nodes that are in the right subtree are 19 and 22. These are all greater than 17. Similarly, consider another one 19, this is the root node, then here it is 22, that is greater than 19. So it is a binary search tree. Now consider another example. So it is only one node, it is 17. So no left subtree is there, no right subtree is there. So it is also a binary search tree, because it has only one node and it satisfies the properties. Left subtree nodes less than 17. So here no left subtree is there, and right subtree nodes greater than 17. No right subtree nodes are there. So it also satisfies the properties of binary search tree, and we can say this single node having the value 17 is also a binary search tree. Now consider this one. So here it is 6 in the root, the left subtree nodes. So 2, 1, 4, 3 all are less than 6. Now here right subtree 8 greater than 6. So for 6 the property is satisfy. Now consider this one 2, left 1, right 4, 3. So all 4 and 3 are greater than 2 and left 1 is less than 2. So this is also a binary search tree. Now consider this one. So it is 60, then its right child 70, 65, 80. So all are greater than 60. Now consider this part, this subtree 70. So left side it is 65 less than 70, and right side it is 80. So it is greater than 70. So left side always chotu, right side always motu. So 65 is less than 70, so it is in the left part, and 80 is greater than 70, so it is in the right part. So it also satisfies the properties of binary search tree, and we can say this is also a binary search tree. Now consider this one. So here instead of numerical values, the characters are there. So here you can see this is D, and the left part or in the left subtree B, A, C are there. So all the A, B, C values are less than D. If we consider the alphabetical order of A, B, C, D like this, or if we consider the lexicographical orders of the alphabets, so A, B, C are less than D. Now consider the right subtree part. So here in the right subtree E, F, G are there. So all the E, F, G values are greater than D if we follow the lexicographical order or dictionary order. Similarly, consider this subtree. Here in the root B is there, and in left A is there, which is less than B. In the right C is there. So here C is greater than B. So this left subtree satisfies the properties of binary search tree. Now consider this one. So here F in the left subtree, E is there, which is less than F. In the right subtree G is there, which is greater than F. So this tree satisfies the properties of binary search tree, and we can say it is also a binary search tree. And the lexicographical order is like this, or the dictionary order is like this: first A, B, C, then D, then E, then E, then G, then H, then I, like this we can continue. So the value of A is minimum here, we can say, and then B, then C, then D, like this. So this is the dictionary order or lexicographical order. So following this order, this tree is also a binary search tree. So here you can observe, like we have discussed, if root value is n, all the left subtree nodes are less than n and all the right subtree nodes are greater than n. So like this we are considering. Then we can say this is a binary search tree, and here we are assuming that all the nodes are distinct or all the nodes contain distinct key values, you can consider, and we are not considering the repetition. So now consider this one. So here 17 is the root value and in the left side it is 22. So 22 is greater than 17, but in this tree it is left than 20, in the left subtree of 17. So this is not a binary search tree, because 22 is greater than 17 and it should be 22 should be in the right side of 17, but here in this tree 22 is in the left side of 17. So it is not satisfying the property of binary search tree. So you can say this is not a binary search tree. Now consider this one. Here it is 17, left side 6, it is okay. So in the left side it contains 6, which is less than the value of 17. Now in the right child the value is 11. So 11 is less than 17. So it should be in the left side of 17. But here in this representation or in this binary tree, 11 is placed in the right side of 17. So it is not a binary search tree. Now consider this one. So here 20 is the root, then left part is 15, 12, 10. So all are less than 20, and in the right side 25, 22. So all are greater than 20. It is okay. So now come to this part, this subtree. So here 15 is at the root. So left part is 12. So less than 15. Okay. So right side is 10. In the right side of 15, the nodes greater than 15 should be present here, but 10 is less than 15 and it is placed in the right side of 15. So it is also not satisfying the properties of binary search tree, and this tree is not a binary search tree. Now consider this one. So here 17 is at the root. So all the left child nodes like 6, 11, 15. So these are less than 17 and are placed in the left subtree. It is okay, no issues. Then for 17 it is 19, the right child, so greater than 17, no issues. Now consider this one, this part. So 6, left child is 11. So 11 is greater than 6. So it does not satisfy the properties of binary search tree, and we can say this is not a binary search tree. Now consider this one. 17, right side it is 19, left 6, 3, 2, 22. So 22 is greater than 17, but here in this scenario it is placed in the left subtree. So this is not satisfying the properties of binary search tree, and we can say that's why this tree is not a binary search tree. So now we are going to discuss about the traversals in a binary search tree. So we have already discussed about the in-order traversal, pre-order traversal and post-order traversal of a binary tree. Now we are going to find the in-order traversal and post-order traversal and pre-order traversal of this binary search tree. So we have already discussed how to find the in-order, pre-order and post-order traversal of a binary tree. So for your recall, I am telling the concept once again in short. So consider this is a node, or you can say this is your friend. So now you are meeting with your friend once and saying hi, then once again you are meeting and going for a dinner with him, and at last you are saying bye bye to your friend. So we are following the direction like this. In this direction we are coming, in this direction we are coming, then we are leaving in this direction. So here we are first time meeting this one. So first time here we are meeting, so I am writing here 1 and we are saying hi, and second time we are meeting and we are saying, or we are going for a dinner, I am writing D in short, and here we are meeting third time and we are saying bye bye to your friend. So we can draw this same hi, dinner and bye structure in this binary search tree. So like here we are coming, so for each node we are meeting thrice, okay. So you can see the direction is like this. So first we are meeting 23, then 18, then 12, then going dinner with 12, then saying bye bye to 12, then going dinner with 18, then meeting 20, then going dinner with 20, then saying bye bye to 20, then saying bye bye to 18. Like this we are meeting, or we are touching each node thrice or 3 times. Now if we want to find the order in which we are saying, or we are saying hi, or we are meeting first time. So we are saying hi first to 23, then 18, then 12, then 20, then 44, then 35, then 52. So now we are going to find the order in which we are going with the dinner, or we are meeting second time. So first we are meeting second time with 12, then 18, then 20. If we follow the direction you can see. So second time first we are meeting here 12, then second time we are meeting 18, then 20, like this. So after 20 it is 23, and then 35, then 44, then 52. So now we are going to find the order in which we are saying bye bye to a node. So first we are saying bye bye to 12, then we are saying bye bye to 20, then we are saying bye bye to 18, then we are saying bye bye to 35, then 52, then 44, then 23. So this order in which we are saying hi, so this is nothing but pre-order. So the order in which we are going with a dinner, So this is nothing but in order, and the order in which we are saying bye bye, this one is nothing but post order. And formally we can say pre-order is like this. In pre-order, first visit the root, then visit the left subtree, then right subtree. I am writing V for visiting the root. And in order, so first visit the left subtree, then visit the root, then visit the right subtree. V I am writing for visiting the root. Then for post order, first visit the left one, then right one, then the root. So formally we can say this is the order of visiting in pre-order, in-order and post-order. Or we can say, or we can draw a line and find like this, the order of high, the order of dinner and the order of buy. So we have thoroughly discussed about the pre-order, in-order and post-order previously in previous lecture. So you can go through that. Okay, so now here you can observe this is a binary search tree. So you can consider the pre-order first, 23, 18, 12, 20, 44, 35, 52, and consider the in-order 12, 18, 20, 23, 35, 44, 52. So here you can observe the in-order traversal is a sorted one. So you can take any other example and you find or you observe that the in-order traversal of a binary search tree is always sorted. The in-order traversal of a binary search tree is always sorted. So please remember this one. And the post order and the pre-order are not sorted, but the in-order traversal of a binary search tree is always results a sorted sequence. Like in this example you can observe, and you can also take some other examples and you can find. Next concept, that is how to find the smallest node of a binary search tree. So consider a binary search tree like this, 25 and it is 15, then it is 30, so here it is 27, here it is 20, here it is 7 and here it is 3, like this. And for 20 it is like 19, you can consider. Okay, so consider this is a binary search tree. So each node satisfies the binary search tree property. So 25, 15, 7, 3, 19, 20. So all the nodes are less than 25. 30, 27 greater than 25. So 15, 20, 19 greater than 15. So 7, 3. So these are less than 15. So 30, 27. So 27 is less than 30. So this binary search, this tree is a binary search tree. Now we want to find the minimum. So to find the minimum, so first come to this root, so it is 25. Then the minimum, so all the values, we know that all the values that are greater than 25 are in the right subtree, and all the values that are less than 25 are in the left subtree. So we want to find the minimum from this tree, and that means the minimum value should be here in the left subtree. So now move to this one. So after checking with this 25, come to this one. Now compare 15. So it has some left subtree and it has some right subtree. So all the values that are less than 15 are in the left subtree. So come to this part, left subtree. Now 7. So 7 has left subtree, no right subtree. So move to the left subtree, because the left subtree values are less than the root. Now 3. So 3 has no right subtree. it has also no left subtree. So we can say 3 is the minimum in this binary search tree. That means how we reach 3? So first reach root, then move to its left, then again move to its left, then again move to its left, and from 3 we cannot move to the left because the left subtree is null for 3. So we should stop here. So here we are getting the value of the minimum, that is 3. Now consider another one. So let us remove this part. Okay. So now consider at the root we have 50, then it is 20, it is 70, so it is 90, it is 65. So assume this is a binary search tree. Now we want to find the minimum. So first come to the root, and it has left subtree and right subtree. We know that the values in the left subtree are less than this root. So come to the left subtree. So here we reached at 20. Now for 20, no right subtree, no left subtree, that means we cannot move to the left here. So 20 is the minimum in this scenario. So in this binary search tree, 20 is the minimum. So how we are getting the minimum value from a binary search tree? So always move towards left. From the root, always move towards left until you reach the null. So until you reach or until you find a node that have no left subtree. So the node that is at the extreme left is the minimum among all the nodes in the binary search tree. Similarly, to find the maximum, so just move to the extreme right, because we know that the right subtree contains the nodes that are greater than the root node. So for consider this one 50. So all the it has left subtree and right subtree. So all the nodes here in the right subtree are greater than 50. So if you want to find the maximum, so just move, consider this right subtree. Now here it is 70. So it has also left subtree and right subtree. So consider the right one or move to the right. So now we reach at 90. So it has no left subtree, no right subtree. So our objective is it has no right subtree. So we will stop here, and this value is the maximum among all the nodes present in the binary search tree. So here the maximum value is 90. So to find the minimum, move to the extreme left, of a binary search tree. To find the maximum, move to the extreme right. So following the same principle, move to the extreme right until we find a node that have no right subtree, like this, for finding the maximum. So now you can consider the algorithm for finding the smallest node. So this is a recursive one, this is a recursive one, and we have also written another one that is non-recursive using the loop. So here you can find the recursive. First we are going to discuss the recursive one. So now consider this algorithm. So the algorithm is find smallest BST root. So this algorithm takes the parameter root, and the precondition is like this: root is a pointer to a non-empty BST or subtree, or you can consider root is a reference to a non-empty BST or subtree, and it returns the address of the smallest node. So in the first step we are checking if left subtree empty, then return root, and of if otherwise return find smallest BST in the left subtree. So, recursively we are using this find smallest BST algorithm. That means if, so consider in the figure like this, we want to find the smallest value or minimum value in this binary search tree, and here the value of root is given. So, the reference to root is given. Now, check whether the root value, the left subtree of this root value is empty or not. So, here you can see in the first step we are writing if left subtree empty, return root. So, here you can observe the left subtree is empty or not. Here in the left subtree one node is there. So, the left subtree is not empty. So, if not empty, then apply the algorithm with or to the left subtree, or here consider this one as root now. So, now if we consider this one, we can remove this one and consider this 20 as root. So, here left subtree is empty or not? Yes, the left subtree of this root is empty. So, we can say 20 is the minimum value, or 20 is the smallest value in the binary search tree. So, this thing we have written in step 1 we are checking if left subtree empty, return root, and if left subtree not empty, then return find smallest BST. That means the same algorithm we are recursively calling, and here previously it was root, now it was left subtree. So, it is a simple one, and here we are assuming that the root is not empty. Now, if you consider the root may be empty, so you can add another step at the beginning. So, in the beginning suppose I am writing at step 0. So, because here in 1 we are starting. So, you can consider in step 0 if root equal to null, or if root empty you can write return root or return root, return null, like that. So, here this step 0 is not there because it is assuming that the root is a pointer or reference to a non-empty BST. Now, if we consider that root may be null or root may be empty, then you can add this step 0 to this algorithm. Otherwise, if you are comfortable with this, then you can write this one. So, it is given in a textbook by Farajan. So, from there I have copied. Okay. So, now this is the recursive approach to find the smallest node or to find the minimum. Now, we follow the same one in a non-recursive approach. That means, we can use a loop. So, we are taking current node equal to root, while current node dot left is not null, current node equal to current node dot left, and at the end return current node. So, after this while loop, return current node. That means, in a loop we are moving towards left until we find the current node dot left is not, or until we find the current node dot left is null. So, the same approach, here we are using a loop, here we are using recursion. So, both are same. So, here loop is used and here recursion is used. Now, find the largest node. So, we have already discussed how to find the largest node, that means move towards right. So, here we are moving towards left. Now, in the algorithm you can write the same one using towards right. So, here instead of previously we are using left subtree, now we are using right subtree. So, if right subtree empty, return root, and if return if it is not empty, return find largest BST on the right subtree. And here if we want a while loop, or if you want to use loop for this instead of recursion. So, here we can write current node equal to root, while this one in place of reft we can write current node dot write is not null, current node equal to current node dot write and return current node. So, if we make this right, this one is for the maximum, and if we write here left, left is for the minimum. So, left is for the minimum and right is for the maximum. So, it is a simple one. So, I hope this is clear to everyone, the algorithm. So, we will implement the algorithm and write the programs also. So, now we are going to discuss how to find one element present in the binary search tree. So, we have discussed how to find maximum and minimum node. Now, we are going to discuss how we will check whether a node is present or not in the binary search tree. Now, consider a binary search tree like this. Suppose it is 50, then in the left part it is 30, here it is 40, then it is suppose 90, 80, so it is 100, then here we can consider it is 20. So, it is a binary search tree. Now, suppose we want to check whether 30 is present there in the list or not. So, we are searching for 30. So, first come to the root. So, compare 30 with 50. So, 30 is less than 50. That means, if 30 is present in this list, it should be in the left subtree. So, we are going to search for 30 in the left subtree, and we are eliminating the right subtree part, or we are not considering the right subtree part because 30 is less than 50. So, now we are going to search in this left subtree. So, in the left subtree, come to the root again. So, it is 30. So, we want to search for 30. So, compare 30, 30, there is a match. So, we can say 30 is present in this list. Now, suppose in place of 30, if we want to consider whether 80 is present in this list or not. So, first consider this root. So, it is 50 and we are searching for 80. So, 80 is greater than 50. So, if 80 is present, then it should be in the right subtree. So, we are not going to the left one. Now, in the right subtree, compare with this one, this root. So, it is 90 and we are going to search 80. So, 80 is less than 90. So, here we are not going to concentrate on the right subtree part because we are searching for 80 and 80 is less than 90, and if 80 is present, then it must be in the left subtree of 90. Now, move to the left subtree. So, it is 80. So, here compare this 80 with the element that we want to search. 80, 80, there is a match, and we can say 80 is present in this binary search tree. Now, consider another one, suppose 75. So, we want to search for 75, whether 75 is present in this tree or not. So, following the same approach, consider first 50 or compare 75 with 50. So, 75 is greater than 50. So, 75 should be in the right subtree. Now, come to the root node of the right subtree. So, it is 90. So, compare 90 with 75. So, 75 is less. So, we should search for 75 in the left subtree. So, here in the left subtree then compare this value with the 75. So it is 80, 75. So 75 is less, so 75 should be in the left part of this 80, and here you can observe the left part is empty or the left subtree is empty. So we can say 75 is not present in this list. So following this approach, you can search for any element present in this list and find whether the element is present or the element is not present. So in each step or in each iteration, we are eliminating one half of the tree, or we are eliminating either left subtree or right subtree of a node. So first we are comparing our value with the root node, then after the comparison we are eliminating either left subtree or right subtree from the searching. Now we will move to the algorithm. So here you can observe, so the algorithm is taking root and target key. Target key means the key which we want to search, and root is the root node. So the precondition is that root is the root to a binary search tree or subtree. Target key is the key value requested, and it is going to return the root node address if the value is found, null if the node is not in the tree. So if found, it is going to return the address, and if not found, it is going to return null. So this is the precondition and the return details about the algorithm search BST. Now what is the step 1? If empty tree, if the tree is empty, so we can say the node is not found and it is going to return null. Now if the target key is less than the root, so move to the left subtree. So we are recursively calling the search BST algorithm in the left subtree part. So we are writing like this: left subtree target key. So previously it was root. Now if target key less than the root, so we are updating this left subtree. Now else if the target key is greater than root, just recursively write right subtree and target key, or we can say we are moving to the right subtree part. Else means if this one is false and this one is false, that means this target key less than root, this becomes false. Target key greater than root, this also becomes false. That means target key is equal to the root. So in this situation we can say we found the target key and return the value of root, and it is end of if, end of search BST. So here recursively we are searching for a node in binary search tree, and if target key is less than root, we are moving to the left subtree. If target key is greater than the root, we are moving to the right subtree. Now consider this one. Here following a loop, we are searching for a node in the binary search tree, or searching for an element in the binary search tree. So the same thing. So here it is recursion, here it is iteration. So while root not equal to null, so here also two elements are given, or two parameters are there, one is root, another one is target key. So while root not equal to null, if root dot element is equal to target key, then return root, and if root dot element is less than target key, root equal to root dot right, else root equal to root dot left and return null. That means after the loop, after this while loop, if the element is not found, we are going to return null. So the same thing, if it is equal, so we are returning root. If we find that the target key is greater than the root element, so we are moving to the right, else we are moving to the left. And after this loop, that means here the loop starts, here the loop ends, and after the loop, if the return statement is not executed, then we can write return null. So, here we are using iteration, here we are using recursion for searching an element in a binary search tree.